Hi, my name is Aran Nayebi, and I'm a new assistant professor to the machine learning department here at Carnegie Mellon. And today I'm going to give you an overview of my work at the intersection of neuroscience and AI to build integrative embodied agents to reverse engineer natural intelligence. So, a great source of motivation for me and the work that I do is that experimental neuroscience is undergoing a revolution in its ability to collect data from larger and larger populations of neurons, giving us an unprecedented opportunity to look inside the brain. In particular, it's becoming more and more common to get whole brain data from awake behaving animals. And so, with this surge in data comes an ever more pressing need of how we're going to go and make sense of all of this data. So the goal of my lab is really to approach this question by reverse engineering the animal brain. And so how do we go about doing this type of reverse engineering? Well, the approach that I've taken in the past is known as task-optimized modeling. And the basic idea is to design machine learning algorithms that are optimized to perform the organism's behavior under the constraints that that organism faces. So in particular, this looks and really is an artificial neural network that's optimized for a particular task or goal that we have in mind. And then the internal representations of that neural network are quantitatively compared to against real biological neural response patterns in a brain area. And the main point is that actually not all, actually many ML algorithms don't end up matching the brain. And the few that do give us two types of outcomes. In particular, they give us a quantitatively accurate and practically useful brain model. In other words, if you have an in silico rendering of the system that's highly accurate, you can then use it to do other things, perform new experiments that were otherwise hard to do in the brain. The other aspect of this is that it also, just from a scientific point of view, gives us principles of why neural responses are as they are. In other words, if we optimize a neural network for a task and those response patterns end up highly matching the brain, then that gives us insight into the selective evolutionary and developmental pressures that gave rise to those response patterns in the brain to begin with. Now, the overarching scientific question that applied this task optimized approach to is how does the brain build and use world models to enable meaningful physical action with the world? And I like to think of world models as consisting of four basic components: representation, prediction, planning, and action. So in my past work, I built high fidelity accounts together with my colleagues in both the primate and the mouse visual systems. As well as going beyond rapid visual recognition to predicting the future state of the environment in both primates and humans. Organisms also plan over long time scales rather than just predict the next step. And so we've studied this and shown that this approach works in rodents as well, and looked at their hippocampus. And an overarching theme of my work has been that if you have a good neural model, then that model also better enables good sensory motor control. So there is a meaningful relationship between a high fidelity brain model and taking actions in the world. But so far, all of these components are good models of individual brain areas, but none of them together form an integrative understanding of any one organism's brain. So in order to interface with the whole brain data that's coming online, it becomes crucial to be able to connect these components and really start to be serious about building integrative agents. But in order to do so, I think each of these components should be improved in a few ways in order to at least start to be able to connect them. So in particular, one main direction that I'm keen to explore is to improve our perception modules to deal with both recurrence and self-supervision to enable sensory learning in dynamic environments. And given the ubiquity of recurrent connections across brain areas, could this enable both multimodal learning as well? Extending our work in future inference to enable more robust inference in the form of more explicit representation of objects, as well as multiple timescales to represent multiple possibilities. Enable generalizable planning to more complex and visually rich environments. Finally, it's known from neuroanatomy that motor cortex consists of highly stereotyped hierarchical and recurrent motifs And a natural question is what functional role does that play? For example, does this enable more sample-efficient motor learning of biomechanically realistic animal bodies, which are known to have very high degree of freedom and are hard to learn and attend RL sense? Now, once we have built this embodied agent, we can actually start to apply it to in a variety of ways. The first thing is that we can, I'm showing here is a schematic of a rodent brain, which is a very common animal from which we are getting whole brain data. And I'm color coding each of the brain areas by the module in the agent that would, for example, best predict it. And so the main point I want to convey is that we're actually going to compare quantitatively each of the modules of our agent to individual brain area responses. And the arrows are a hypothesis for how those brain areas actually interact to enable complex behavior. And so the main point is that we're leveraging the nexus of two advancements in AI to build functionally predictive hypotheses, and advances in neuroscience to strongly constrain those hypotheses by grounding them in real empirical predictions of the brain. And this yields a series of practical outcomes. First are open source benchmarks that the community can use. But one main outcome is to actually be able to predict outcomes for new experiments. Now we have an in silico rendering of an animal brain. We can go and run that millions of times more cheaply than actually doing it in the biological system. And finally, from a scientific point of view, it gives us a systems level understanding of an organism. And what I mean by that is that it allows us to interface with questions that otherwise would have been hard to do. So for example, we can start to study the hardwired intrinsic goals that enable animals to autonomously survive in complex environments, which is computationally a hard problem because unlike reinforcement learning in games, these goals are not well specified in many of the environments that animals are in. We can also start to understand the learning rules that are in the brain. So I've done a lot of past work on this, but this agent program really helps get this learning rules off the ground by starting to study how these modules interact to enable learning of new tasks that can go and be compared to animal data. Lastly, this enables us to study much more deeply species-conserved algorithms across these modules. What I mean by that is that this sensory motor loop that I'm talking about isn't restricted to any one animal. For instance, it's not restricted to the rodent, but many other animals share the sensory motor loop from flies to zebrafish to macaques and infants. And so here, what I'm schematizing here are the brains of three different species, rodents, macaques, and humans, and highlighting the homologous brain areas that are involved in the sensory motor loop as a schematic. And the main point is that this agent program is naturally extensible to start to study the sensory motor loop across these and gives us a detailed computational understanding of the shared principles, if any, between them. So most notably, no robot exists today that's as autonomous and adaptive as biological animals are. And this is an aspect of where natural intelligence truly shines, and that neuroscience and AI can learn virtuously from one another. The brain science of the future will heavily leverage machine learning to build functional and predictive theories of natural intelligence. So if you're interested, please feel free to reach out, and thank you for your time.